video is going to help you identify strong and weak bases. Let's start with the strong base. Like the acids, if you have something strong, the forward reaction predominates and the reverse reaction is just mild. A good example of this is sodium hydroxide. You could say that the hydrogen from water, since it can act as an acid or a base, a hydrogen from water gets kicked over here and produces water, and what's left over is sodium plus and hydroxide minus. Because the arrow pushes in the forward direction, we have more of this, okay? Notice we have more of the ions on this side. As a result, my ionization is said to be complete. This correlates to the conductivity being good. The only way that I can move around electrons is to have charge. So I need to have charge in there in order to have good conductivity. The conjugates of sodium hydroxide, they would only differ by one hydrogen. So this would be the conjugate. This would be the base because it has one less hydrogen, and this would be the acid. We're going to call this the conjugate acid because it's on the product side. Noting that the arrow here is small, we're going to call this weak. And then the sodium hydroxide, because its arrow is big and long, this would be a strong base. A weak base would have the forward reaction being small and the reverse reaction being quite large. There's actually two examples of this. The first one I'm going to do for you is NH3, which is ammonia. NH3 plus H2O. In this case, NH3 is a Lewis base. So the N has dots. So we can take one of the hydrogens and put it on here, make an NH4+. I hope you recognize that as ammonium. And what we would be left with is OH-. Okay? If we look at this reaction, once again, we would find that because my arrow forward is really teeny tiny, I would have less of this, which would mean very partial ionization. That, if you look at it, because I wouldn't have that many ions in solution, my conductivity would be poor. The conjugate for NH3, notice that the NH4 has one more hydrogen. We're going to call this the acid. Because it's on the product side, we're going to call it a conjugate acid. Because my arrow is big and long on the product side, I'm going to call that a strong conjugate acid, thus making NH3 a weak base. Notice, again, the OH- is really what we determine for what's a base. Because I don't make that much OH-, I'm going to call it a weak base. Another interesting example would be sodium hydrogen carbonate. Remember, this is baking soda. NaHCO3 is baking soda. That's a good weak base, and you're going to want to have that around home just in case you've got to neutralize an acid. If we take the hydrogen from the oxygen, pull it over, we're going to get H2CO3, which is carbonic acid, plus OH- plus Na+. If you'll notice, this pushes way far to the right. Sorry, way far to the left. One thing I want to show you about this one works just like the other one. But when you put sodium hydrogen carbonate into water, this thing is going to dissociate. You're going to have Na plus HCO3 minus. As a result, you will have ions in solution, and your conductivity for this one would be good. Okay? No matter how you look at it, you're going to have ions in solution with that one. So that one's kind of a tricky one. Again, the conjugate acid and base works, the partial works. Let's go ahead and go up here to number 3. NH3 partially ionized. This word right here indicates to me that it's weak. And I know that NH3 is a Lewis base. Okay, having the dots. Hope that helps. Look at them a couple of times. See you in class.